A2 Further Maths, Area of Polar Curves. Right, so just a quick recap from last year. What I'd like you to do, please, is have a go at plotting the polar curve r equals theta plus 1 between 0 and 2 pi. Just see if you remember how to go about drawing these polar graphs. Okay, so pause there, have a go at sketching it. It doesn't need to be perfect. You've got an idea from the polar graph paper there. I don't expect you to have polar graph paper in front of you, so you could just have a go at just doing a rough sketch of it. Just get an idea of what it looks like. Okay, so pause there until you've got a sketch. Okay, so hopefully, as you remember from polar graphs, it's all about sticking in different values of the angle and seeing how that would affect the R value. And the R value, of course, was the magnitude, how far out you go. So it's not to do with X's and Y's. Okay, so you can ignore the X's and Y's. It's all about trying to work out how far you go round and how far you go out. So in this case, when I look at theta equaling 0, which is straight across here, then the R value will equal 1. So it's definitely got a point just there. As the R value goes round, so we can see here that's going to be pi over 2, so that's pi over 4, so roughly pi over 8. When you get pi over 8, that's going to be 1 plus pi over 8. So it's going to go out a bit more, and so on. So what you get is you get this curve going round like that till it gets to this point, and as you can see, this is 2 pi plus 1, which is why it's a bit bigger than 7. Okay, so you can see that the curve spirals round like that. Okay, so you practiced those sorts of skills last year. Now what we're going to do is we're going to extend on that by looking at area under polar curves. Okay, so that's slightly different to how you go about working out the area under a Cartesian graph, because now you're going to deal with polar curves. So what we're going to do is we're going to look at the difference with polar graphs. Now, as you know, if you're looking for the area under a curve, you'll have in your head how you do it for Cartesian graphs. And so for a Cartesian graph, for example, if you were looking at the limits between 0 and -2, you would draw lines straight up to the curve and you'd work out the area under that curve like that. Now for polar graphs, it's slightly different. Your limits become your angles. Okay, you're still working out the graph below that limit, all right, so below that curve, but you're looking at setting your limits going from the origin point out at given angles. So in this case, I'm looking for the area between theta equaling some number alpha, whatever value that is. It looks like it's about pi over 4 there, up to theta equals some other angle, in this case beta. Right? Again, looks like it's pi. It's going to be 3 pi over 4 roughly in that sort of direction. Okay, so what I want to do is I want to work out what this shaded area is. Now, if I'm going to approximate it, if I'm going to just estimate that area to start with, what I'd like you to do, please, I'd like you to think about which shape is the most appropriate. Now, when we did it before, we talked about maybe trapeziums or rectangles. What sort of shape would be appropriate if you're doing a polar graph, would you say? Okay, so hopefully you thought of, it's not appropriate to do rectangles because you can't really fit them. You're sort of going out from the origin up to these points, and each time you're taking a slice. Now each slice looks roughly the same as a sector. So if you imagine you're going to cut it into sectors like this, okay, and see that the sectors, they're quite thick, those sectors, but it's not a bad approximation. I can approximate it using sectors. And the good thing about approximating using sectors is I know what the area of a sector is because I've done that in normal maths. I know that the area of a sector I can work out. Okay, so I can approximate the area using these types of things, these sectors. So in this case, I've worked out the area between rough estimation, the area will be 1 to 6, the sum of each of those individual sector areas. So that's what I've got so far as a rough estimation. Okay, so I can improve that, and you know how to improve it. You can improve it by increasing the number of sectors. And the more and more sectors you have, the closer and closer it's going to get to that approximation. Okay, so if I want to just improve that, then I can increase the number of sectors. So the question now is, what's the equation for the area sector? So if I asked you that question, what's the equation for the area sector? Hopefully you all know it off by heart. It's got nothing to do with polar graphs. It's got to do with what you did last year with when you did radians. What's the area of a sector? You would know it's half r squared theta. Okay, that's the area of a sector. I say it's nothing to do with polar graphs, but you can clearly see in there you've got the sorts of language that you do with polar graphs. It was just never connected at that time. R being your radius, theta being your angle. Okay, they are connected to polar graphs in that way. So the area of each of those sectors is going to be half r squared theta. Okay, so what I can do is I can replace that r value just there for r squared theta. Now what's important is I'm looking for a change in the theta. Now what I've done there is I've halved the angles. I've just halved the angles. So you're changing that theta value. Right, that's the thing that's varying. The R value is worked out from each one of those. So you can just do it from R values. But the formula there is half R squared theta. Exactly the same. Where you're looking for a change in your theta each time. Now our goal, of course, is to make that theta value as small as possible. The smaller we get that value, the closer and closer that theta value tends towards zero. And as n tends towards zero, if I look at the limit of this summation, it's going to become an integral. We've seen that plenty of times now, where the summation tends towards zero, so therefore it becomes an integral. So how can I write this as an integral? I could write it as a half r squared d theta for your change in your theta value between the limits alpha and beta. So I'm starting at alpha, I'm going to beta, I'm changing that theta value by a very small amount each time, and I can work out the r value for each of those, square it and half it. Okay, so that's where this formula comes from. So in your notebooks then please. So rather than me just giving you the formula, I've shown you, I've demonstrated where that formula comes from. So given a polar curve, defined in terms of theta, so r equals some function of theta, and the area is enclosed by the curve between these two limits, alpha and beta. So there's our two limits. We can find the area using that formula, half r squared d theta. Okay, so make sure you got your notebook, make sure you got down what you need, pause if you need to. Okay, so what I'd like to do is I'd like to actually go have a go at working out the exact area that I showed you a minute ago. So I've got the r equals theta plus 1. I want to work out the area enclosed by that curve and the half lines theta over 4 and 3 pi. Pi over 4 and 3 pi over 4. So that's the graph I've got, and this was the area I was referring to. So it goes between pi over 4, that's one of the half lines. There's the other half line, which is 3 pi over 4, and I'm looking for the area enclosed in those three curves. So that one, and that one would give me this area. So how do I go about doing that? The first thing I'll do is write down the formula. So in this case, the formula is A equals a half r squared theta or d theta between alpha and beta. And I can fill in some of the parts of this formula I know. The r squared, for example, comes from this formula. So in other words, I can replace the r for theta plus 1. The d theta will stay because now I can integrate it in terms of theta because I'm replacing that. The alpha and the beta can get replaced for pi over 4 and 3 pi over 4. And so once I substitute all that in, it turns it into an integration sum that you're more than used to. You can integrate it however you want. Okay, you can expand it if you want to, or you can integrate it like I've done using the inverse chain rule. It's up to you. So once you've done that, you can either do it on your calculator or just do it yourself. We have an area of approximately 5.35 units squared. Okay, so you can see how you can work out the area under a polar curve. So just take down what you need, pause if you need to. Okay, so I'm going to write down the polar equation, or I'd like you to write down the polar equation for a circle of radius 5. See if you remember how to write down the polar equation for a circle of radius 5. Okay, so if you forgot, it doesn't matter, it's not the end of the world, but the answer is just r equals 5, which makes sense because whatever your angle is, Okay, so whatever your angle is, you just go out 5, you're going to produce a circle of radius 5. So it's very easy to plot a circle in a polar curve. It's a lot harder to plot a straight line on a polar curve. So you can plot a circle by doing r equals 5. So if I want to work out the area of that circle, okay, the area of that circle, and I use the formula that I do normally, I notice that the r squared is going to be 25. What I want you to do is to show me that the formula actually works. It actually gets you the area of the circle you expect, which of course is 25 pi. Okay, so have a go at that yourself. Okay, so hopefully you substitute the 5 in, you got 25. You integrated 25 in terms of theta. Okay, so you integrate 25 in terms of theta, and that's going to get you theta. You also notice that your starting limit is going to be 0, and you want to do the whole of the circle. So you want to go all the way around from 0 to 2 pi. We want the whole of that circle. All right, so starting and finishing at the same point. So once I've done that, I've got 25. I'm going to get 25 theta. I can put my two values in. So I can put 2 pi in, which is going to get me 25 times 2 pi times a half, which is going to be 25 pi. And of course, putting naught in cancels it out. So I'll get my 25 pi as required. It's just nice to see that for a simple polar curve like that, that the formula does get the answer that you expected. It does work. Okay, so in your notebooks, please grab down this exam question and by all means pause it, have a go yourself on a rough piece of paper. I'd rather you not do it straight in your notebooks. I'd rather you wait and see the model solution, but you can certainly have a go at it yourself. In fact, I'd want you to have a go at it yourself first of all. Okay, so we've got a drawing there. You can see we've got the polar curve. We've got an equation. I want to find the region bounded by the curve C. In other words, you want all of that area, that shape. Okay, all of it. So how could I work out the area inside that shape? Okay, so I'll pause, give you a chance to get down what you need. A quick sketch wouldn't go amiss either. Okay, so let's see how far you got then. So hopefully you thought about your limits. Because you want all of it, you want to go from 0 to 2 pi. But that's not the only option. Okay, so if I asked you what else you could do, hopefully some people out there might say, well, you could actually do 0 to pi, and due to symmetry, you can just double it. And that's perfectly reasonable. In fact, sometimes that's more helpful, which we'll come to in a second. Okay, so you can go from 0 to 2 pi for the whole lot, or you can go from 0 to pi and work it out and then double it. It's up to you. Not really going to make any difference in this case. What's my R value? Well, it's going to be that, so I can substitute that in. I need to be careful and think about how to do this integration, but by now you've practiced a lot of different integrations, so hopefully this shouldn't be too tricky for you. So I can expand this out, that's one option. I can definitely integrate that really easily. I can definitely integrate 25 really easy. Cos squared, okay, so if I asked you now how to integrate cos squared, hopefully you'll tell me you need to be looking at double angles. So we can use double angles to get cos squared. Okay, the double angle formula is like that. Cos 2 theta equals 2 cos squared theta minus 1. Why is that helpful? Because although you can't integrate cos squared that easily, you can very easily integrate cos 2 theta. Okay, so cos squared theta is a bit of a pain, but cos 2 theta is very easy. So I can rearrange it. Just double check you're happy with that. So if that was 16 cos squared, I'd get a minus 8 there, and I'd have 8 there, and of course I can take the 8 to the other side. So that's where that comes from. Okay, I haven't changed that and haven't changed that, so I'm still waiting to do the integration. But now I'm in a position to integrate it, aren't I? Because this integrates nicely. The 8 and the 25 can go together, the 40. So there's no reason why you wouldn't be able to integrate that now. I've just put the 8 and the 33 and the 25 together. So the integration I get will be 4 sine, because of course cos integrates to positive sine. It differentiates to negative, but it integrates to positive. That one integrates from cos to sine, and of course 33 d theta doesn't just disappear. You're not differentiating, goes to 33 theta. Can I work the answer out between 2 pi and theta? Hopefully you can, and you get 33 pi. Okay, so very well done if you managed to do that exam question. It seemed fairly straightforward because the integration wasn't too bad, but it's all about using this formula just here. Okay, so what I'd like you to do is have a go at sketching the polar equation r equals cos 2 theta. So again, you can just do it roughly. See if you can remember what that looks like as a rough sketch. And just be aware of the limits. So I want it from 0 to 2 pi. But most importantly, I'm only interested in when the r value is greater than 0. So we talked about negative r values last year. And in this case, anything time we get an r value of negative, ignore it. Just don't plot it. Just plot the r is greater than 0 part. Okay, so pause there. Make sure you do have a go at getting that curve. Just keep plotting the theta values till you remember what it looks like. Okay, so we have a look what you should have got. So in this case, we should have found that when you've got the r values substituted in, you should have got something like that. This equation with 2 petals on either side. Okay, what I'd like you to do now is, now you've got an idea of what the graph looks like, I want to find the area that's enclosed in that graph. Like it says there, find the area enclosed in that curve. So again, pause it, have a go at using the formula, see what you get. Okay, so I'm looking for that area. The problem with this solution, or what is the problem with this solution? So when I go through it, I've worked out the area from 0 to 2 pi, which seems reasonable because that's my limit, so you might have done the same. You've got cos of 2 theta squared. Okay, now I can deal with that because I can use the double angles formula that I mentioned a minute ago. In this case, it's going to go to 4 theta. So I could do that. So hopefully you could just double check that yourself. You can see where that comes from. Once I've got that part and got that from there to there, then what I've done is I've worked out the integration. I've substituted the values in and got pi over 2 as my answer. Perfectly reasonable. You may have written that down. No issues at all. All right, not issues at all. But the question is, what is the problem with that solution? Now, the problem with that solution is that pi over 2 is too big. You might be able to see it. It might not be really obvious to see it there, but the answer is it's too big. And the reason why it's too big is because although I ignored the negatives in this case, if I didn't ignore the negatives, what would happen is I'd have 2 more petals here and here. And when you did the area from 0 to 2 pi, it included those negative values. It included those 2 values just there. And it does it automatically. So you need to be very careful because I still want you to work out the area of this bit just here. But the trouble is you've worked out the area of those 4 petals like that. So if I asked you now, what is the area I should be looking for? Hopefully you'd say, well, now it's pretty obvious. You've got pi over 2 is all 4 of them. So if I want just 2 of them, it's just going to be half of it, which is pi over 4. Okay, so you can do it that sort of way. You just need to be careful. The other option, and the more important option, is being able to work it out without having to work out the whole thing and then having to think, what do I do to work out the answer? And the reason why it failed is because it worked out an area in this region just here, and it's not what you wanted. So what you should do is you should work out the area of a single petal. If you can work out the area of a single petal, just this petal just here, then you can multiply it by whatever amount you need. In this case, it would just be doubling it. Rather than working out the whole lot, it's a lot easier to do in that. And if you remember, to work out the area of the petal, we use what we call the tangents to the pole. So we're working out these numbers just here. Okay, so in this case, I can see that the tangent lines were going to be pi over 4 and minus pi over 4. So if I work out between those two lines just there, what I'm going to get is the area of a single petal. Now it's the same maths as what you just did. There's no difference there. Same integration, just different limits. So I can still do the same bit of maths. There we go. I've integrated those two. I can substitute the pi over 4 in. I can substitute the minus pi over 4. Out comes pi over 8. What do I do now? I say, well, I don't want just one of the petals, although you might have been asked that one petal. I don't want the one petal, I want 2 of them, so therefore I can double it to get the area that is required. In this case, pi over 4. Okay, so be very careful when you're working out the area of polar equations. It's always a good idea to work out the single petals when you have these types of polar graphs. Okay, so what I'd like you to do, please, is I'd like you to show that r equals 2 sine theta can be written like that. So that's a bit of practice from last year as well. Could you show me that that could be written like that? And because you could do that, could you then have a go at working out the sketch of the curve? Because hopefully you can do it from the Cartesian. And can you work out the area of it? And you don't need to use the polar equation formula for that, although I want you to as well, please. Okay, so I'm going to repeat what I just said. Can you convert it? Could you sketch it? You should be able to sketch that straight away now anyway. Can you work out the area, because you can work out the area really easily from that formula and your GCSE skills? But could you also work out the area by using r equals 2 sine theta in the polar curve, the area of a polar curve formula? Okay, so pause there, have a go at all that, please. Okay, so hopefully you've sketched it. Hopefully you've worked out the area using that, and hopefully you've used the area doing this between 0 and 2 pi, and you've noticed there's a problem. If you didn't notice a problem, you haven't done one of those bits. Okay, so let's have a quick look. So the general formula, this is converted from there to there, is knowing that y equals r sine theta. So I know that y equals r sine theta. I could rearrange it, and that tells me that r equals 2 sine theta would go to 2y over r on this side. I get r squared equals 2y. So that's what I could get in that side. And then from there, I know that r squared as well is x squared plus y squared. So because it's x squared plus y squared, what I could do is I can replace this side for x squared plus y squared. And so then I could just rearrange this, and I'm going to get 0 equals x squared plus y squared minus 2y. Now this bit, I can complete the square, okay, to get it into this sort of form. So if I complete the square on this part, I get this equation. And why is this equation nice? Because I can clearly see it as a circle. It is a circle with a center point of 0, 1 and a radius of 1, which is why I said to you, you can work out the area without having to do the polar equation. So if you didn't do that already, work out the area of this circle and compare it to the answer you get when you've worked out the area of this using the polar curve formula. Okay, so let's have a look at what you got then. So there's our sketch of our circle. Okay, you could have done it with either polar or Cartesian. So there's a sketch of our circle. And if I want to work out the area of that sketch, I know because the area is pi r squared, this has got a radius of 1. So therefore the area of this, really easy, is just going to be pi. It's definitely got an area of pi based on that circle just there. The problem is, although there's nothing wrong with this sketch and there's nothing to do with r being negative, when I tried working out the area of this curve just here, I do this, 0 to 2 pi. I should do 0 to 2 pi. It's important to cover the whole all the way around. I get 4 sine squared theta. Fine, nothing wrong with this. Oh, I can use the double angle formula again. You know, I've used that a few times now to get 1 minus cos 2 theta. Okay, so I can use the double angle formula just there. If you're wondering where the y4 goes to that, of course, I've put the half in. So double check you're happy with that. So half of that gets you 2. And then I can use this directly. So I'll get that answer. I get that solution just there, and out pops 2 pi. And if you check the maths in there, there's absolutely nothing wrong with the maths. It's a solution that's just wrong. And the reason why the solution is wrong, you might be thinking, oh, that's because you ignore the negative and down here should have been another circle. Now that's not true. Okay, there wasn't another circle down here, because if you tried doing something like putting in, let's say, we got around to pi, so maybe 4 pi over 2, something like that, or 4 pi over 3. We could try those sorts of numbers, and what we find is that any of these values become positive. They get you this value, so you get a circle as you go round. But then when you get underneath, what happens again, although you do get negative values, they don't draw it down there. They actually go straight over the top of the circle again. Okay, this circle gets drawn twice. Once for the positive values around there, or once for those from 0 to pi, and then once again for pi to 2 pi. So although you can't see it, and although it doesn't look anything wrong on the graph, you've actually drawn the circle twice. And when you worked out the area between 0 and 2 pi, you actually counted the area twice. You did 0 to pi, that counts as one circle. You did pi to 2 pi and counted as another circle, hence why you doubled your answer. So it's the same problem as before, except this time it's a lot harder to spot. Okay, so it's important to make sure that you only do it between the limits of the graph. All right, in this case, we want to do it between 0 and pi. So in this case, as we said, we get a circle from 0 to pi, and we get an identical circle from pi to 2 pi. So when we did the integral, it doubled the area. All right, so both of those examples were where you get errors. Okay, so just grab your notebooks then, please. Let's just put some of these important facts down. So we need to try to remember them from when we come to our own questions. So when you're calculating the error of a polar curve, we need to have a really good awareness of whereabouts the limits are. We need to make sure that we don't include parts of the graph twice, or maybe we include part of the graph that we shouldn't be including. So it's really important to make sure that you consider your limits so you don't make this mistake. Okay, right, so you could probably have a quick sketch of that. It doesn't have to be a perfect sketch, but a sketch of that graph just so we can refer to it. So if I want to work out the area of this curve just here, and I did it from 0 to 2 pi, what's going to happen is I'm going to actually include these more than once. So I'm going to quite have a problem. Yet if I look at it and I knew the area of just one of these petals, it'd be very easy for me to say, right, now I know one of the petals, I just times it by 3 and there's my answer. And that is what you need to do. Now the problem with trying to work out one of the petals is whereabouts to set your limit. Now you might look and think, I'm going to set this limit from 0 to pi over 2, okay, because that's definitely going to include that petal just there. The problem is, if you went from 0 to pi over 2, okay, from 0 to 90 degrees, what's going to happen is you're actually going to include this section of the petal here, okay? Because with all these values in here for theta actually get you a negative answer. So you wouldn't just include this petal, you'd actually include an extra half of a petal as well, right? So this limit should not be pi over 2, it needs to be this value coming off here. Now we've already referred to this already, but you looked at them last year. They are what are called tangents to the poles. So the tangents to the poles are what give you your limits. Now for people that have forgotten what the tangents to the pole is, you might be better off going back and looking over previous lessons. But you can also, just as a reminder, work out the tangents of the poles because you're looking for where the R value approaches 0. Okay, so the R value doesn't equal 0, it starts to approach 0. You can see that here, look, it goes off from 0 there, comes round, starts to approach 0 just there, and forms a tangent. Okay, so you need to work out what the tangents to the poles are to be able to work out the petal in between them. Okay, but once you've got your limits, you can use your integration formula, you can work out the area of one of those petals, and then multiply it by whatever you need because of symmetry. Okay, just pause there, make sure you've got done what you need. Okay, so on exercise 7a on page 169, just gives you an opportunity to practice some of those skills, just be awareness of your limits, but also just making sure you can use that formula correctly. Okay, so make sure you have a good go at those. All right, so what I'd like you to do, please, I'd like you to practice these bits on your own to start with. So I would like you to have a go at working out the two shaded areas, as it says there, those two separate questions. All right, so pause there, have a go as best you can on both of them and see what you got. Okay, let's have a look at this first one then. So we're going to look at this graph just here. We can see that we've got an area that's not just enclosed by some poles, but it's also enclosed by two graphs, two polar curves. Now, if this was a case of trying to do this with integration as normal, what you would do is you would find the integration of one of the curves, and then you would take away the integration of the other and find the difference between them. This isn't quite the same when it comes to polar curves, because if you look, what you're actually doing here is, as you're working around, you're actually finding the area of this red curve up to this angle just here. So between 0 and whatever this angle is here, you're finding the area of the red curve. Once you get past that line, all right, that angle just there, you're then working out the area of the blue curve. So instead of doing one take away the other, it's all about finding out what this limit is. The other limits you're dealing with, you can see, is 0. We can see that this curve here, the tangents to this pole are going to be 0 and pi over 2. Okay, so it's all about working out from 0 up to this line, and then from this line up to pi over 2. The question is, what is this angle just here that intercepts just there? We need to find that point of intersection. So the point of intersection, of course, is when the two R values, as you can see there, are equal. Any other times, they're different. These two different there, different here, but they're equal there. They've both got the same R value. So I could set those equal to each other. I could do a bit of rearranging. Okay, so I get that. Just be aware, don't just divide by cos theta. It could equal 0. It doesn't in this case because we're not interested in equaling 0, but it could do. So we're looking at, and the reason why you're not interested in the cos theta equal 0 because it equals 0 down here. So we're not interested in that. What we're looking for is what value this would be. Okay, so 1 minus 2 sine theta equals 0 gets you an angle where we get a half of pi over 6. Okay, whereas cos theta, of course, when does cos theta equal 0? At pi over 2, and you can see that's true. At pi over 2, the blue curve and the red curve do also equal 0 just there. They intersect at that point. But you don't want that point. You want this point, which is where the sine theta equals 0, hence pi over 6. Great. And hopefully now it's drawn in, you can sort of see it makes a bit more sense. Between that line and this, we want the red curve. And between that line and pi over 2, we want the blue curve, okay, filled in. So we're working out between 0 to pi over 6 and then pi over 6 to the other one. If you want to pause and have a go at finishing that yourself, by all means do so. You don't have to wait and listen to the rest of it. You can have a go yourself. Okay, right, see how far you got then. Okay, so let's see how far you got then. So I'll calculate the enclosed area of the two polar curves separately. So this one here is from 0 to pi over 6, which is what I've just calculated where they intersect. And you can see now that this is going to be just this red curve. Just the red curve, that section just there. It's got nothing to do with the blue curve at all. All right, so if that blue curve wasn't there, it'd still be that same area. So I'm interested in the area between 0 and pi over 6 for the red one, which is where this comes from. And on the opposite side, I want the blue curve. And again, if the red curve wasn't there, this would still be shaded in. You wouldn't have any issues with that at all, from pi over 6 to pi over 2. Okay, so I've got that part of the curve. Now all I need to do is have a go at doing these integrals. Okay, so I can work them both out, do them both separately. So this one's going to get you, I can see actually, this is quite nice, isn't it? Because 2 cos theta sine theta, of course, is a double angle. So I could just write it as a double angle formula straight away, which is going to get me this one squared. The half and the 2 have cancelled out, which is where you've got suddenly got the 2 on there. Oh, 2 squared, be careful. 2 squared is 4, half of 4 is 2. That's where that comes from. I can use my double angle formula again. So keep using the same formula, which is great, good practice. So I get 1 minus cos 4 theta. All right, for that one. And for the other one, all right, it's going to get me 2 cos squared theta. Same issues again, but this is 2, so on the front, so that's quite nice. It was 4, it was 2 squared is 4, half of 4 is 2. That's going to get me that value, which I can put in as well. So I've got my 2 values, which you can take your time and make sure you're happy with. Once you've got the values for both of those, I've got exact form, which is always a good idea to keep it in exact form. So once I've got the values of those two, lo and behold, pi over 2 minus 3 root 3 over 8. Very well done if you managed to work that out. If you didn't get it in exact form and you got it as a decimal, it's not the end of the world. You would get the same answer. Okay, just be aware if they're asking for it exact form. Okay, so how did you get on with the other one then? If you want to pause now and have another go or have a go at it, that's fine. Let's see how far you got then. So on the second one, it's a little bit more interesting because if you try to work out from 0 to 2 pi, what's going to happen is you're going to include this section just here. You're going to include it actually added on. So you're going to work out the whole of that big section, including that filled in. Then when you get down here to these two values, you're going to include that shaded in section again. All right, so we need to be really careful with this one. It's very easy to make a mistake and forget that this has actually been included. Right, it needs to be taken away. So first thing I need to do though is think about where these tangents are, where these lines. Because if I can work out where these lines are, it looks like it's really easy. It looks like it's there, but it's not, is it? It's just a bit beyond it. So I need to work out the tangents to the pole. Okay, so when I work out the whole lot, so if I work out the whole area, what I'm going to get is I'm going to get, I expand it, I'm going to get this, I've used the identity, none of this should be new, okay, so all of this you should be able to do by now. You can see the same thing coming up all the time using this double angle formula. Work it all out pops an answer of 3 pi. Okay, that's nice and neat. So the area of the whole thing is 3 pi. But the problem is, when I worked out 3 pi, I've not just included this section just here, right, when I went round and did, because I did this bit first, and that definitely includes it because it's inside it. But then when I got round here, instead of doing this bit, it went up here and did this. So I actually included this area twice, all right? So I need to be very careful, all right? As it says there, include the area twice. So what is that area? And if I know it included it twice, I know I can take it away. So what? Okay, so what we're going to do is we're going to just look at the tangents of the poles. So it's a nice little recap from last year, if you've forgotten. The tangents of the poles is where this R value is going to come in and start to reach 0. So the difference between the pole and your value is going to approach 0. So the way we do that is by replacing that R value for 0. Right, so we can just write 0 equals 2 sine theta plus 1. And that's going to let us know what this theta value actually is when R is starting to approach 0. So if I substitute that in, I rearrange it, just be aware that once you get the answer to this, the answer becomes out to be minus pi over 6. Now minus pi over 6 does make sense, because it's down here, but it would be better for you, once you've got your minus pi over 6, to think about your secondary solution, to think about what solution it is to go over here, okay, which is going to be pi over 6 added onto pi. All right, so you've got to consider both of these by knowing that one value from there. So I can see that 7 pi over 6 is another solution, and 11 pi over 6 is yet another solution to sine theta equals minus a half, and they're the correct solutions that I actually want. Once I've got these two equations, these two tangents to the poles, I can then use those as my limits. I can work out the areas from 7 pi over 6 and 11 pi over 6. So both of those. So I can work out both of those values just there. And that's going to get me area this middle section because it's the area between there and there. And hopefully it's going to be smaller than 3 pi. It's pi minus 3 root 3 over 2. So that's the area of that small blue section. But the problem was it was included here. So I definitely need to take it away then. But it was also included between these two. So I'm going to have to take it away a second time. So my actual answer by using symmetry was the original 3 pi, take away one of these when I went from there to there, and take away the other one when I went from there to there. So my final answer is pi plus 3 root 3. Not straightforward, a lot of thinking about symmetry, and you need to have a really good awareness of what's happening as that angle changes as the graph is getting plotted. Okay, so pause if you just need more time on that. Okay, so have a go at the exercise 7b. These are the more technical questions, the ones that involve you finding out the areas between certain poles, certain polar graphs. So have a go at all that exercise and make sure that you have a go at some of the tough ones and are asking for help when you need it.